Welcome to our Stratasys webinar today on From Prototype to Production, how to choose the best composite 3D printer.
I am Rachel Rakowski. I'm an applications engineer at Stratasys. I've been at Stratasys for about 6.5 years now, and I have been working on the FDM material products team.
And I'm John Hedlund, and I've been at Stratasys for about 12 years. I'm a senior mechanical design engineer. And I've had a long history in 3D printing. I've been started out in college at a service bureau and have worked many jobs in 3D printing along the way until I ended up at Stratasys. So today for our agenda, we're going to hit we'll have 5 topics and then question and answer at the end. And those topics are the material performance and availability. And basically, not all carbon fibers created equal. Second topic is critical components and features needed for composite printing. And again, carbon fiber printing requires additional equipment considerations that you normally don't think about. Third is repeatability and reliability. And so end use parts, which are normally in composites, require a higher level of printed part requirements. The fourth topic, the build volume and throughput. So how many parts do I need to produce and what can I produce? Fifth topic, ease of use. So does it take an expert to produce carbon fiber parts, or are the printers easy to use? And then lastly, we'll have the question and answer. And so for the question and answer, we will address questions at the end of the presentation. And if you have questions, please feel free to type them in the chat box to be addressed at the end.
To start us off, we're going to talk about what is the difference between chopped carbon fiber and continuous carbon fiber, because these two aren't identical. So the chopped carbon fiber, we have short segments of carbon fiber that are intermixed within the material, versus a continuous carbon fiber is laid down so that it's continuous within the part. So we lay down some substrate of the plastic, and then within one of the layers, we start to lay down a continuous fiber that runs along the length of the part. So that's shown in the bottom image next to where it says continuous fiber. So the white material there is the polymer, and then it's laying down some continuous fiber that's running the length of the part. So the chopped carbon fiber has some advantages. It improves the strength of the part over a non-filled material of the same polymer type. And it can help to reduce the warping of the material while also increasing the heat resistance. And then it adds the strength in any place where the material is within the part. So because the chopped fibers intermix within the polymer, that strength increase is in all those areas. The disadvantage of the chopped carbon fiber is it's still an anisotropic within the material. So we see it helping more in the XY or the build plane than we do in the Z direction as we stack up those layers. And then depending on how much carbon fiber we have added into the material, the surface finish might be rougher. So we have a nylon 12 CF material, and that is a little bit rougher material than our nylon CF 10, just because it has a much higher amount of fiber within the material. For the continuous carbon fiber, it does a really good job of increasing the strength and stiffness in the direction of the carbon fiber. So let's say all the carbon fiber is running along the length of the part, and we're applying a load in that direction. It's going to be really advantageous there. But then we start to see the disadvantage of perpendicular to that fiber, we don't have that increase in strength from it. The continuous carbon fiber, it also adds complexity to printing it. So systems would have one head to lay down the polymer and then one head to help lay down that carbon fiber, but then you have to cut it. So it's just a little more complex there. And then we also have to deal with the adhesion of the carbon fiber to the polymer. So it's a little bit of a decrease in the Z strength due to the weaker bond strength as far as that goes. Another factor of the continuous carbon fiber is that it's very geometry dependent for the pathing of the continuous carbon fiber. So there's a minimum bend radius and wall thickness that you have to work within. So the example up in the upper right-hand corner, we start to be limited by how thick those areas are that it's not able to fill that carbon fiber all the way to the end for that most inner path. And then another thing with the continuous carbon fiber is that it's not able to cross over itself. So you can put it, but you kind of have to have a mentality of where does it go. So this is something that you should consider as you're buying a composite 3D printer, is what kind of carbon fiber you're going to have in there. At Stratasys, we currently just have the chopped carbon fiber, but some of our competitors do have the continuous carbon fiber. At Stratasys, we have a very transparent and consistent test procedure for the mechanical testing of our FDM materials. So we have our material data sheets, which lay out a number of different mechanical properties, including tensile, compression, flex, and izod impact, as well as physical properties such as heat deflection temperature. For a preferred material, which is quite a few of our materials, each data point for like the tensile strength represents 30 specimens. So we have 3 machines with 10 specimens off of each machine. So we're seeing a breadth of data to get an idea of the expected performance of the material. For a validated material, which includes the Kimya PCFR and a few of our other newer materials, we have a minimum of 10 specimens from 1 machine that are required. It's a little bit less extensive of testing there. For our materials, we test both the on edge, so that's where the XZ or orientation, so kind of you can see it in the middle of the orientation pictures in the upper right hand corner, and the upright. So the upright is our weakest orientation because we have shorter tool paths stacked on top of each other. But the reason we do that is to just give a very transparent expectation of what our expected material performance is. We also have a standard tool pathing that we are using for this. So we're just doing our standard 45-45 as shown to the left. So each layer stacks up on top of each other with all perpendicular layer or rasters to the previous layer. All of this can be found within our Stratasys material testing procedure document. We'll have a QR code later on if you want to take a look at that. So one thing that we have seen that a lot of our competitors do for testing is they're testing unidirectional tool paths. So for this, all of the tool paths are aligned along the length of the part, so shown as in the upper right-hand corner. So this shows us what the maximum possible strength in the material is, especially for fiber-filled materials. But it's not representative of a large part or a typical part that's printed. It's just the highest possible strength that we see out of the material. So it's kind of cherry picking the best data. And so for this, all the contours, it's all aligned toolpaths. It's basically all contours printed in the flat orientation. And from one of our competitors, you've even seen where they do a racetrack loop around the part and then cut off the ends to so that you have the right size sample, but then it's all contours. So what we recently did is we did a study where we used their print methods. So we printed in the flat orientation, so the on edge and upright, and then aligned all of our tool paths to see how does our data compare to the competitor data. So let's jump to the next slide and take a look at that. So the data on this slide shows the results of the study where we're comparing the standard tool pathing to unidirectional tool pathing. So within the table, we represent both tensile and HDT data. So the tensile is where we are pulling a mechanical dog bone on both sides, and we're evaluating the material's strength, ductility, and elongation. HDT, or heat deflection temperature, is the temperature at which a material starts to soften or deform under a load, indicating its heat resistance. It evaluates the maximum strength the material can withstand without significant deformation or failure. Typically, at Stratasys, we've been reporting the as molded data. Here we have both is all as printed data. Within the table, the far right column is the competitor data. So that's one of our competitors' materials as they report it out on their data sheet. The far left is our data sheet data, or since we typically share the on-edge data and upright, we actually printed out the flat data using our standard procedures of the 45-45 rasters there to have a comparison point. And then the middle column is the unidirectional data for nylon CF10 following our competitors' procedures. Within this data, we see a very significant increase in the performance of the nylon CF10 material when we go from our standard toolpathing to unidirectional toolpaths. We see a 152% increase in the modulus of elasticity and a 94% increase in the yield strength for the tensile yield strength. So these are not insignificant. We are practically doubling the performance of the material. For the heat deflection temperature, when we go from the standard tool paths to the unidirectional tool paths, we see a 160% increase in the line tool paths. For the tensile test results, the nylon CF10 has higher tensile modulus and tensile strength, whereas the competitive materials have greater elongation at break. This is a trade-off. By increasing the material's strength and ability to withstand deformation at a given force, the amount of give or ability to elongate is decreased. The tensile modulus of nylon CF10 is roughly twice that of the competitor's material, indicating that the Stratasys materials are stiffer and able to withstand greater forces with less deformation. If we were to look at our data sheet, if we were presenting the flat orientation of the material, for the elastic modulus of elasticity, for our standard 45-45 tool pass gives about the same data as what the competitor's unidirectional data does. But when you use the same test methods, we go up to about 6 gigapascals, or more than twice that of the competitor's material. So just showing that the tool pathing really makes a difference in the performance of the materials. For the heat deflection temperature at 0.45 megapascals, the competitor's material data sheet reports 145 degrees Celsius, which is less than that of the nylon CF10 with the unidirectional tool pass, which is 153 degrees Celsius. The competitor does not provide the performance for the HTT at the higher pressure, so the 1.8 megapascals, but Stratasys tested their material on their machine at that higher pressure for HTT. And for that material, the HTT at 1.8 megapascals was 105 degrees Celsius, which is a 31% decrease in the HTT temperature from the lower pressure for the material. For nylon CF10, there was only a 13% decrease in the HTT temperature with the higher pressure. So we also did test their material at the lower pressure and got a similar result to them. So what we're seeing is they have more of a drop off with a higher pressure during the heat deflection temperature testing. And so, but they're not reporting out that higher pressure result. So just something interesting to know, just the breadth of data that we offer by showing both the low pressure and the high pressure on our data sheets. So in all, it was interesting to just see how much of an increase we saw in our material performance with the unidirectional testing and how much that changed when we're comparing it to competitor materials. The materials look pretty similar when we compare our standard tool pass to their unidirectional material or their unidirectional tool pass, but when we test in the same manner, just the significant increase in our material performance is just something that needs to be taken into consideration of really, as you're looking at comparing between different systems and different materials, you need to understand the test method and use that to choose the material. So when looking at a composite machine, one thing to look at is what materials are tuned for that printer. Are the materials ready to use, or is it something that's going to require manual adjustments? The user needs to be aware of what materials have presets versus what they will be responsible for doing the tuning of the materials. At Stratasys, we have several materials on our F123 CR systems that have thousands of hours of tuning to give the user success. So these are materials that are ready to drop on the machine and use. You don't have to take the time to figure out what temperature it needs to be extruded at or how to get it to print well. We've done the work for you to make it much easier to do. So these materials range from ABS M30 to FDM TPU 92A to our composite materials of the ABS CF10 and FDM nylon CF10. So these are materials that have carbon fiber within them and are tuned and ready to go on the machine. Another thing to think about when looking at composite machines is what are the applications that you're going to use the material with. So for applications that we'd expect for carbon fiber materials. We would expect to see tooling in all sorts of manufacturing facilities and industries. And this is because it can take advantage of the high strength and stiffness applications of these materials. Some other applications that we could see it in is rapidly producing low run tooling. So soft jaws, forming dies, machining fixtures, drill guides, and end of arm tooling are some examples that we've seen. And it can also be used to reduce the part lead time. So to have CMM fixtures to hold another part, or CNC work holding fixtures, or surrogate parts. When we go to the next slide, we'll see one of our use cases for a CNC work holding fixture, but these are all just different ways that we can use these materials. And so just keeping in mind, like, what is my application, and making sure that it'll meet the applications as you choose the machine. So this is a use case for a work holding fixture for a CNC. So a tool shop manager had the choice of using additive of 3D printing or subtractive CNC processes to produce soft jaws as a work holding fixture for metal tools that had been used on the production floor. It is assumed in this case that the end part must be made of metal by design due to the length of production runs or other considerations. The CNC operator has studied the tool they are going to make and determined it would need custom work holding soft jaws to complete the operation in the CNC machine. So they're starting with this circular ball of material and figuring out how are they going to hold it, and realize that they needed soft jaws for it. So when looking at the process, they realized there would be more steps to get through creating a holding fixture for it in the CNC than using the 3D printer. Additionally, by using a 3D printer, the labor time is 20% of that of the traditional machining labor time, so an 80% labor time savings. The traditional machining took over 5 times more operator hours and cost more than 8 times more in labor alone. So a 42% reduction in cost per part using the Stratasys 3D printer to create this part, partially due to the difference in labor costs. And it gave them the ability to redirect their skilled machinist time to more profitable operations. So using Stratasys is effective and proven soluble support. You can print what you want, not what you are limited by other processes. So the soluble support helped enable this application. And the biggest advantage for 3D printing is more complex parts. And so you're able to sometimes combine more tools, 2 tools into one, and accomplish more with less. So it's an easy iterative process with low learning curve. So here they were able to take what might have been previously CNC'd for a work holding fixture, 3D print it, save time and money. So a great application. And it was enabled by having the carbon fiber filled nylon CF10 material.
Another critical component or feature to look for in a composite printer is hardened components. So one thing you have to know is that carbon fiber filament is extremely abrasive. All of the carbon fiber fibers act like sandpaper. And so that filament, as it goes through the system, the tubing, the gear, and the nozzle will wear on all those. And so you can see to the picture upper right of a brand new nozzle on the left. Typical nozzles are in brass. And then on the right is one that after only 250 grams of material, which is about a quarter spool. And you can see extreme wear in the length and also the diameter. And so one thing to know with tips and nozzles, as little as 250 grams can destroy a nozzle. Worn nozzles cause poor layer adhesion. So first layer is the height. As that nozzle wears down, that height's not accurate. And so you're not going to get the proper amount of squish of material to the build platform. And so therefore, it's not going to adhere and you're going to have delamination. And then worn nozzles also result in poor print quality because of that difference in height, difference in geometry, difference in diameter. You're no longer putting down paths with a known dimensional accurate nozzle. And so now you can have paths that are wider than you want, plastic going in places that you don't want, and so part quality suffers visually. The extruder gears, people don't realize how much wear the carbon fiber filament puts on extruder gears. Look to the right, those gears are supposed to be straight. You can see that there's a path worn into that gear. And so that results in under extrusion or loss of extrusion. That gear can no longer bite into that filament and push it. And then the last thing is the tubing and connectors. The fiber wears those also, even the Teflon tubing, and especially in a Bowden style where the filament is pushed into those tubes, it wears more. And then lastly, okay, you say, yeah, I bought a printer and I bought hardened components. Not all hardened components are equally hard. And so some that are labeled hard are maybe, yes, a little bit harder than the brass, but not very hard at all. And so some hard nozzles are good for less than 4 kilograms of material, which isn't a lot, typically around 4 spools. The Stratasys Nylon CF10 extrusion head, which you see on the right, which includes the nozzle, includes the extruder gears, and it's just a drop-in replacement. They're designed for 1,500 hours of printing. And what that means is, under typical use and typical parts, that's about 29 kilograms of material. Depending on what you print, it could be a little bit more or a little bit less. But 29 kilograms of material is a significant amount of material for a single print head. And that's because we design with very hard materials, and it works very well. So another consideration is the support. So you have soluble, mechanical support options. And so support removal is important with carbon fiber parts. So the most common support option is same material support. You're creating support out of the build material, and carbon fiber itself is meant to be stronger and stiffer. And so, of course, support in a stronger, stiffer material means it's more difficult to remove. Geometry can work with same material support, but complex geometry is almost impossible. Same material support relies on a gap layer between the model and the support material. And so they basically have a skip a layer printing so that you don't have as much adhesion between the support and the part. And that results in poor down-facing surfaces because you have that gap, and what happens is when the hot material gets put down, it will droop into that gap. And so it's not good for small features, and it's not good at angled walls because it just doesn't adhere to those angled walls and those small features. Dedicated breakaway support is a better option. Dedicated breakaway support means it's a different material that can be removed from the part because it allows decreased bonding. And so that makes it easier to remove. It's better, it has a better interface quality because you no longer have that gap layer between the part and the support, but it is limited for complex geometries. So, where you have trapped geometries and lots of little holes and other things, it isn't as good for. But what it results in is faster time to part. So you have flat surfaces, you have simple areas to take off. You can see that green part there is kind of an example of a dedicated breakaway support. It just peels away. Stratasys does offer a dedicated breakaway support. It's called SUP 4000B. And that's for the nylon CF10, and in the geometries and parts that works on, the time to part is really quick. And then lastly, we have soluble support. And soluble support offers just a great solution for complex geometries. And a lot of printers out there, other than Stratasys, their soluble option with a nylon CF is a PVA. And the problem with the PVA support is that it's very, very moisture sensitive. And once moisture gets into that PVA, it basically wrecks that PVA. And the thing that happens is PVA is also very heat sensitive. And so if you have PVA material that is stuck in a nozzle or in a nozzle that's heated, it's very easy to plug that nozzle. And so PVA doesn't end up being a very good solution because it's very finicky and you can have a lot of reliability issues with printing. The Stratasys support, on the other hand, has been designed to be reliable, and it allows complex geometries. And so you get very good part quality. It takes that time to remove that soluble, which typically, with removing the part, putting it in a tank of liquid, and then drying that takes about a day, half a day to a day longer. But you can get, like you see on the left side, a very complex part. You can have support removed without wrecking the part and still have very good surface quality. Another critical component or something to consider is a heated build volume. And what a heated build volume can do for you is it can give you higher accurate large parts. And so the way it does that is that a heated environment lowers the internal stresses in a part, reducing curl. So you can see curl in the two of the graphics on the right, the green part. So those edges are curling up. And then in that blue part where it's delaminating from the build plate because of stresses in the part. So by heating the part, the stress in the part is reduced, and that does reduce the curl. Heated beds are what some of the printers use to try and simulate a heated environment. And that is effective in a low Z height part. But what happens when you get above a few centimeters is basically that part is not seeing any effect from that heated bed anymore. And lastly, what is most common with their non-heated environment, and parts in that kind of environment with no heat are less accurate as the size increases because of curl. So less curl means prints won't delaminate. Less curl means prints are more accurate and they're more repeatable. Another aspect of the heated build volume is increased Z strength. So one aspect with carbon fiber is that as the content of carbon fiber increases in a part, the Z strength actually decreases. And so in a non-heated environment, your carbon fiber parts are going to have lower Z strength than your model material would be without the carbon fiber. And so when you have a non-heated environment, what happens is you print a layer and that layer is cooling. And by the time you get back to printing another layer on it, that layer has cooled so much that you don't have very good entanglement or bonding between those two layers. The heated chamber, what it will do is it will keep that part at a higher temperature. And so that when you put that new layer on top of the previous printed layer, you have better polymer entanglement, which gives you better Z strength. And so a heated environment is much better for Z strength in carbon fiber parts. And so the Stratasys F123 series utilizes that heated build volume for higher accuracy, higher reliability, and improved part strengths. And I'll just point you to the graphic on the right of the exploded printer. And you can see that there's a build chamber in the center, and that build chamber has insulation around it. And it was specifically designed to allow uniform temperatures across the part, across the print plane. And that really results in a superior part due to accuracy, reliability, and part strength. One common thing missed with carbon fiber materials is their moisture sensitivity. Most carbon fiber materials are nylon-based materials, and nylon absorbs moisture. And spools can become wet or saturated with moisture in as little as 24 to 48 hours. And what happens when a material becomes wet? You get reduced visual part quality. You get oozing, stringing, and bubbles. And you can see that the top two graphics on the left, that's stringing between a couple towers. And then because of oozing too, you just have less control over the output. And so it can give visual artifacts and rough surfaces based on that printing. Another thing people don't consider is that a wet material lowers the mechanical performance of the part. So when you have oozing, when you start a new layer, that new layer has less material in that nozzle, and so you under extrude the beginnings of the tool paths because a lot of that material already oozed out of the nozzle, and so it isn't there to be put into the part. And then there are voids, there are bubbles and voids and gaps that are in that part because of oozing, because of bubbles, and those voids also reduce part strength. And so most printers have no way to control moisture. I'll let you know that Stratasys F123 series has ways that they combat moisture, and they do that in 3 ways. The materials ship in a pre-dried airtight packaging, so they're sealed and they come dried. You don't have to dry it like you would with most material that you get from competitors. Secondly, there's a sealed dry box in the printer, and if you look to the left, that is a picture kind of the dry boxes with those tops open. And then there's desiccant in the hub of those materials that do active moisture removal. So as you have moisture that does enter into the system, that desiccant removes that moisture. And so with those 3 methods, it's very effective in getting rid of moisture, and essentially you get a better looking and stronger part because there's less moisture.
For system reliability and repeatability, at Stratasys, we have done a rather extensive study on our machines to look at how are the systems performing over time and how repeatable are the prints. So for this, we have about 3 to 4 weeks of printing to start it off, followed by a 4-week break, and then 1 week of printing again to compare back to the beginning. That 4-week break, we might be printing other materials, or the machine might be idle depending what the demands of the lab are. From this, we print mechanical coupons as several increments across this time, as well as a dimensional part that I'll show in a little bit. And then there's other physical and challenge parts that we're able to look at to see the part quality. So we will jump into how the dimensional and mechanical performance is over time in a little bit, but first we're going to look at the system reliability. So this is looking at how parts / jobs are produced correctly on the first try. So any system error that caused the build to stop was considered a failed job. Any part that finished and was deemed acceptable part quality was considered a good part. If some of the parts finished on a failed job, they were considered good parts. The first pass part / pass yield is a percentage of parts produced correctly on the first try versus the number of parts / jobs that were started. So I was looking at how many parts are made correctly without a system error. So for our systems for the F370s, we did a total of 4 printers in this study, and we did it with both ASA and ABS. We also had a couple of competitor systems that we did an internal study on. We had 2 of their machines, and we used the competitor material for it. So looking at the data for the first pass yield, for ASA, we have a 99% part yield, and then a 92% for the ABS CF10 for the part yield. The competitor material and competitor machine gave us a part yield of 87%. So one would expect that the first pass yield numbers would decrease with printing with continuous carbon fiber. So we weren't using continuous carbon fiber for this, but if we were, we would expect the first pass yield numbers to decrease as the carbon fiber prints, continuous carbon fiber prints with the secondary extruder, and increases the chances of misalignment, fiber adhesion issues, and nozzle clogging. The Stratasys prints were done with a second extruder for the support material and still show much fewer failed jobs. So we are performing very well. We have the data that are able to show the reliability of our machine. And a lot of our competitors, they don't have this data and they haven't done this study to be able to show you how the machine looks performing over time. Let's jump to the next slide and I'll show you what our mechanical performance looks like. As mentioned within the study, at several increments throughout the build process, we printed mechanical coupons. And so this is looking at the mechanical strength of ASA on the F370 over time. And so what we're showing with these graphs is that for both orientations, we are repeatable over time and we're reproducible between machines. So each color represents a different machine, and the data is clustered that we're seeing very consistent results off of each particular machine, as well as pretty well clustered data between each of the individual machines. This is not data that our competitors would have, and so this is something that's unique to Stratasys to be able to show the repeatability of our machines mechanically. Looking dimensionally, we show a similar story. So we have this 9-inch check part. So it has features that range from about 1/8 of an inch up to 9 inches in size that we're able to measure on a CMM to see how it measures dimensionally. So this part was printed at several points in time throughout the study as well. And once again, we show that we are repeatable over time, particularly on a given machine, and that, but it's also reproducible between machines. Of we see less than a 5/1000th of an inch variance between the different machines as far as it goes. So we are showing that our machines are reliable, or that our F370s are reliable and repeatable over time. So this is data that very unique to Stratasys, that we have this data and not something that you would have from our competitors.
All right, so another question in considering a carbon fiber printer, composite printer, is my build volume usable? And that's probably a question you've never asked. And what about build volumes do you need to know? And one is it big enough to fit your parts, the number of parts you're doing, or the size of the parts you're doing? But what people don't realize is your entire build volume usable? And what do I mean by that? Is that build plates are not flat a lot of times. And you take a look on the left, that is a scan of a build plate. And you can see that it's higher in the center and there are low spots in it. You would have trouble printing over that entire area. There's a kind of a sweet spot in the middle, but outside of that, the parts are not going to stick. You're going to have adhesion problems, and with different ways that the build plates warp and are not flat, sometimes you can have nozzles that plug because of a build plate's higher at certain points than other points. First layers don't adhere, and you can't print parts at the edges. And so the other thing to consider is the non-heated print volume means that you can't print as large parts as you want. And we talked a little bit about that earlier, what the advantages of a heated build volume is. But essentially is, as you get larger in a non-heated print volume or area, you are going to get inaccurate parts, and you get lower Z strength. So if you want to print large parts that are accurate and strong, you need a heated build volume. And that means that parts that you print in a non-heated build volume, you're going to have to reduce that size of those parts because of build plate flatness and because of the non-heated print volume. And so again, just looking to the left, that lower picture that's a sample print from a F123, and you can see that they're printing to the extreme edges, and that we're having success. And so Stratasys printers are designed for a flat and usable build print plate that even at the edges can be built on. And then with a heated chamber, it's consistent across the build plane, resulting in large parts that are accurate and strong. And so those are just some different aspects of build volume that you need to look at when considering composite parts. When looking at your parts, is how many parts can I produce? And a lot of people are using carbon fiber for manufacturing or producing parts that they're going to use. And so you need to have a printer that can produce the parts you need and the number of parts you need. And so you need to ask, how many parts can I get off this printer? And it determines how many printers are required. And so do I need to buy one? Do I need to buy more than one? And you need to know that printing carbon fiber can be slower than printing PLA or ABS. And so just looking at it, Stratasys F123 printers are faster printing most materials than even composite materials compared to the competitors. And so we did a throughput study on this end of arm tooling. You can see in the upper right. And so what we did is we printed that build tray on a Stratasys F370CR in nylon CF10, and we printed those same parts on a competitor with continuous fiber. So just one thing to note is, with most of the end of arm tooling, jigs, fixtures, thin layers, while they sometimes increase part visual quality, they don't necessarily increase the part functionality. And so thin layers aren't beneficial for the jigs, fixtures, and tooling. So when we do a throughput analysis, you can look on the right. And so we track build time, number of parts per build, the builds per week, and the parts per week. And so what we basically said is, hey, I've got one shift. I'll start a print. When that print's done, I'll start another print, and I'm only working, 8 hours a day for 5 days a week. How many parts can I get off that printer? And so with the F370CR at 7 thousandths of an inch layer heights, you can get 6 parts per week off of it. And at 10 thousandths of an inch layer heights, you can get 10 parts a week off our printers. The competitor printer, you could only get 3 parts per week off that printer. And so over 5 years, you can see that we can produce a lot more parts. And so basically, the F370CR at 7 thousandths of an inch layer heights has twice the throughput of the competitor. And at 10 thousandths of an inch layer heights, it has 3.3 times throughput. So if you put that another way, you would need 4 of the competitors' printers to print as many parts as you could off of a single F370CR. And so that makes a difference with just running one printer, or do you need 4 printers? And there's a cost that's incurred with having more printers. Another thing to consider is how hard is this printer to use? So as we talked about earlier, carbon fiber wears components and nozzles, and those components become just wear items that will need to be replaced. And so even the extruder gears will have to be replaced. And so most printers need the user to be mechanically inclined. It's up to you to order the parts, to get the parts, and to change them yourself. And then on top of that, once you've changed these components, you have to manually calibrate. So you're going to have to manually load, unload material. The nozzles, a lot of times they recommend, and to get them off, need to be hot. It requires a special tool. And then when you're putting a new nozzle back in, putting heat paste on and torquing the new nozzle to the correct torque. And then you have to calibrate manually the Z height. And if there's 2 extruders, you have to calibrate the tip to tip distances so that you have correct alignment of the materials to each other. And with extruder gears, it involves significant disassembly. There's a picture there, it's kind of an extruder that's been disassembled to get to the extruder gear. And then you're going to have to calibrate that extrusion output from that gear, because each gear could have a little bit different size, and it could act a little bit differently than the gear that you had previously. And so you have to manually calibrate that extrusion output. Well, if you look on the lower left, there's a picture of one of the Stratasys heads in its carriage. And so the 3 things you have to do to replace the Stratasys head is just unclip that ribbon, that electrical connection, pop out that filament connection, that little yellow plastic tube there. And then there's a lever that you open up, and you can basically pop the head out, put the new one in, latch the lever, put the electrical connection in, pop back in that tube, and you're done. The printer is going to take care of all of the necessary calibration automatically. That extruder gear and that nozzle is in that print head, and so you don't have to worry about that. That has already been calibrated. And then the tip to tip and Z height gets done automatically by the printer. And another nice thing is Stratasys printers will let you know when maintenance is required. So it will let you know when the life of your components are at that time that need to be replaced. Whereas with these other printers, you're going to have to manually guess or manually check, and maybe you're suffering poor print quality, and then you'll say, boy, I'm getting such bad parts off there, I need to replace components. So a couple last things. How hard is it to use with materials? If you look on the upper right, how many people that have printers are dealing with spools of material where they don't know how much material they have left on the spool? Do I have enough material to print the part that I need? And so most printers do not keep track of the material volume on the spools. And so it becomes very difficult to know if you can produce a part, and if that printer is going to stop, or if it doesn't have a filament out sensor, it won't stop, and you'll basically be printing in air and have to reprint the next day. So Stratasys printers know exactly what material is loaded. You can see in the middle there, there's a screen. It tells you what type of material is loaded, how much material is remaining, and you know, even if that spool has been removed because you switched to another material, you put that spool back in, it keeps track of that material volume. So another nice benefit to the F370 CR is that it has auto changeover, and there's the bays on the lower right, and you have 2 for model material and 2 for support. And so what happens is you can have a partial spool and you can print with that partial spool, and when that spool is used up, it will automatically switch or change over to a full spool in the next bay. And so you don't have to track the volume of material. You don't have to worry that that might stop printing. If you're printing over a weekend, you can have enough material to print everything that you need. And if you're having to dry material before each print on these other printers, it's really hard to keep track of the volume of material that is on that spool. And so with auto changeover, you lessen that worry about, will my part be there in the morning when I need it. Hopefully we've covered these 5 topics, and we'll just recap those. So the material performance availability, you know, not all CF is created equal. Not all carbon fiber is created equal. You need to look at and make sure you're looking at apples to apples data. You know what you're looking at. Is it aligned tool paths? What are the conditions of that testing? And so understanding what the terms of the testing is important to understanding what your material performance is. And then the portfolio of materials you have. Are they tuned materials that are just ready to go out of the box and you don't have to change settings and experiment? Or are they materials that you're going to have to become an expert at and tweak along the way? And then the applications. Make sure that your material meets that application need and that higher performance. Make sure that why do you have a material that meets those needs for that application? And then 2 critical components for composites. Remember that hardened components are important. The support solution is important. Heated build volume offers a lot of peace of mind for accuracy and reliability. And then a moisture solution. You're going to have to deal with moisture one way or the other. You might as well let the machine deal with it versus having to manually dry before every print and worry that your part is taking too long and your material might become wet during the build and you'll have poor print quality. Number 3 was the repeatability, reliability. Just the amount of data and the amount of work that Stratasys has done and produces to show that our parts are repeatable and reliable is just not done anywhere in the industry. And so if you care about your parts and your parts are important, and you should be looking or asking, what is the reliability? What is the repeatability? Am I printing with a known commodity? Number 4, the build volume and throughput. What is the size and number of parts I need to produce? And can I do that on the system that I have? Or do I need a different system? Do I need more systems? And so that's an important aspect. And lastly, ease of use. What are you responsible for? Does that user have to become an expert at changing components? Or does the machine do most of the work for you? Is it easy? And then do I have to keep track of materials and have spreadsheets and have notes and what do you have to do to be able to print without worry? So hopefully we've answered all those questions. By the way, here are a couple QR codes for the test procedures for Stratasys materials and the unidirectional testing that we've done to show the difference between basically how the competitors test versus how we test, and if we tested like a competitor printer test, how our material performance data goes up. Thank you for attending the webinar, and Rachel and I will address the questions that you guys have. All right. Thanks for joining the webinar, and we'll do the Q&A now. The first question we have in is, where should I use composite materials versus PLA or ABS? And that comes down to what properties the chopped fiber give to the material. And so the fibers really increase the heat deflection temperature, and so higher temp uses. And then the fibers also increase stiffness and strength. And so, you know, PLA is actually has high tensile and high stiffness at a low temp, but anything above 40 C, it gives up. And so anything basically in a little bit elevated temperature at all, it's not worth anything. And so, and ABS also has better durability, but it doesn't have a very high working temp. And so higher working temps, higher performance with the tensile, with stiffness, is where you want to use composite materials.
I can take the next question, John. The question is, are you planning to do unidirectional testing of other materials? So for the unidirectional testing that we did of nylon CF10, we also did on ABS CF10, and we plan to do on nylon 12 CF at some point in the next 6 months. So this is something that we are doing for our carbon fiber filled materials only, and we will be adding it to the data sheets for those materials.
Next question is, isn't continuous fiber a much better option than chopped fiber? And that really comes down to your part geometry. Continuous fiber is very good in the direction that the fiber is laid. And so in tensile, continuous fiber is very strong. But when you start in torsion and in other directions, continuous fiber doesn't really do much for reinforcement. And continuous fiber has limitations of geometry limitations because of turn radius, and also the layer length, or the length that the continuous fiber, minimum length you have, the width of the fiber that you have to put in. And so chopped fiber can go anywhere where you put a toolpath in. And so it does a much better job in complex geometries. It does a much better job in anything that basically isn't like aluminum plate replacement. And so chopped fiber does very well. You can align the fibers for chopped fiber with the unidirectional toolpaths, and it basically emulates the continuous fiber properties also. Continuous fiber is ultimately stronger, but the use cases for it are a lot more limited. Next question is, dovetails into this, is should I always use aligned toolpaths? And that depends. If you want to strengthen specifically certain directions, then aligned toolpaths work well. And in thin walls, in thin parts, aligned toolpaths work very well. But if you have a bigger part, or a part that needs strength or torsion stiffness, you know, for twist and bend in multiple directions, then having like a 45-45 infill pattern, cross pattern, makes it much more quasi-isotropic, so semi-isotropic, versus if you have aligned toolpaths, a lot of times it makes it anisotropic, where the strength is greater in one direction versus another.
The next question is, would a different head be needed to use for nylon CF10 versus ABS to print the materials? And the answer is yes. So nylon CF10 has a hardened head, but as John talked about during the webinar, it's very easy to change the head. So there's only 3 steps, and then the printer does the rest of the work. So it's a very quick change out to go between heads.
Next question is Stratasys dedicated breakaway really any different than other printers' same material support? So it is. And so Stratasys has a dedicated breakaway, and what that breakaway, how that is different is that it's tuned to release very easy. But because it's a separate material, you can print directly on top of it and it will release. And so with these other same material supports from other printers, they actually try and skip a layer to reduce the bonding to the support layer to the part layer. And what happens is you get a worse part quality on that because the part droops onto that support layer. And so you get better surface quality with dedicated support. You get a better breakaway, and more complicated geometry releases. And what's the benefit of a dedicated breakaway is getting a part directly out of the printer, taking a minute or two to remove supports. It's a great thing, and you can have it right away. Where dedicated breakaway doesn't work is if you have trap volumes, large or deep holes, and very complicated geometry with sometimes the designed morphology, where you have generative design, makes it a lot of little holes and almost like a lattice structure, and that's where you would use soluble support.
Can we trade in our vintage Uprint SE? Yes, we do have a trade-in deal for older machines. The best thing to do is going to be to reach out to your channel partner for details on the program. And that looks like that concludes our questions for the Q&A session. Thank you again for taking the time to tune into the webinar.